Welcome to Rogue Bit. We're doing the full playthrough of the game with explanation of every puzzle. Let's start a new game. So we play as this single bit who is able to move 1 byte at a time across memory. See? This is me. So let me just check something. Yeah, okay. So we are the 7th bit of this byte, and we are moving to adjacent bytes. As you can see, I cannot pass through here, and you can see on the left side the 7th bit is set for those bytes, so I cannot enter them. This is important. You can see if the 7th bit is set when the byte is marked with this bluish color. And you can also stand. You see, this byte is, these bytes here are empty, and this one, the dot one, has you see, I'm adding myself there. So dot and my byte, which is 64, when they add up, you get the small letter N. Okay, here's an explanation of the binary and decimal numeral systems. So basically we have the binary on the left, and we don't have decimal basically anywhere except the player position on the top of the screen, and the rest is in hexadecimal, which we will explain just a bit later. So this is the first puzzle. We cannot go through these because letter A would zero us. You see here, this byte here becomes 0. This bit becomes 0. And here we can see player plus dot. You see, when I stand on the dot, it becomes the letter N here. This will be useful later. There's a puzzle which uses exactly the dot character and N. So if you see that, you can recognize this combination. Okay, and here we have a first interesting puzzle. Why can't we go through here, you see? Because these characters are not your regular dot that you would place at the end of the sentence. This dot is in the center. It's used to denote multiplication in math. And we cannot go through these. And here we have equal sign, minus signs, which have different ASCII values. ASCII is basically bytes used to store characters in memory, and we can go through those. Same here, we have underscore, which has the 7-bit set, and we have these interesting characters which don't, so we can pass through them. Okay, and now we have a first complicated puzzle. So looks can be deceiving. Actually works for this part here and for this part down here, and it also works because it's dead end here. It works for this part here. If you notice on the left hand side, those bytes beneath me, below me, you see, don't have the 7-bit set. So I can enter through here, and now no way to go through here, so we're going through here. Now this here is the whole ASCII table, all 256 characters, and we're gonna find our way. So this is a dead end. I'm looking at the left side of the screen, you see. We're looking for a gray path, so we can enter here, and then we could go down, but it's a dead end, so we're going this way. Okay, nice. And now this is a dead end, so we're going down, and I can already see all the way down. I can pass and leave the maze. So that was the, I don't know, third puzzle, but the first serious puzzle. Okay, here's a short explanation of hex, or short for hexadecimal. Basically, it's a system with 16 digits. So 0 through 9, and then the letters A, B, C, D, E, F are used as digits 11 through 16. And you can see the player coordinate. You see, like, it's 40, 40B, 41, 40B, 42, 44B, and we go to, after 4, 9, it won't be 50, it will be 4A, B, C, D, E, F. The player coordinate is on the top of the screen, the red one. Okay, so these will use the player coordinate to determine the coordinates of other stuff on the screen, and this red thing I picked up means that the CPU will start executing a program. We can see a very simple program on the left. It swaps the byte at E25D, which is here, you see, E25D, loads that into data register and swaps out the contents of the data register back. So there's that X letter, if you see X letter, it goes into the register, and then the program jumps back to the start, and now it swaps again, so it returns back. So it goes back and forth. If we stand here when this is empty, we can swap ourselves into the data register like this, and now we're in the data register. We cannot do anything there at this point, so we'll just press any of the arrow keys, up, down, left or right, for program to continue and swap us back out. We're back. Okay, so when I stand on the red square, the program changes, and now we have a simple teleport. It swaps between those two locations. If you press B on the keyboard, you can see that on the top of the screen, by the way. In the top right corner, you see need help. Hold B to highlight addresses. So if I hold B, I can see the jump address of my program above me, and I can see the two swap addresses. So basically, if I go here, I will first be swapped into the data register. There I am, top right, you see data register, value 40, which is exactly my byte. And now the next statement will swap us onto the other side. Here we are. And now we switch to another program. Okay, So this one swaps the address 7654. We have to find where that is. So we are watching the player coordinate at the top of the screen. 76. We're going down to 76. Okay, 7654. So it's above us. 5B, 57. So it's we have to go around. Okay, so it's 7653, and below us is 7654. So if I stand there, it swapped me, and now it's gonna swap me into the next section. 5A, 5C. Okay, I'm here, and we're changing the program. Now an interesting thing happens. Okay, so this is dead end, but there are a bunch of swaps happening here. If I press B, I can see them, but let's try to do it without pressing B. Okay, so 495C is here, and if we stand there, it's just gonna take us into the data register. Okay, swaps to 5A, 5C, which is where we came from. Yeah. Okay, so standing here at 49 doesn't help. The next address, there are two more addresses. It's 3F5C and 2959. So this address here is 35 horizontally. So 29 is to the left. This is where we want to go. So we probably have to stand here. 3F5C. We got 5C, so we just need to find 3F. Here it is. Now I want to stay here and get the program to get to that swap instruction. So I'm just gonna press up or down to make new instructions, make CPU to execute new instructions. Okay, here it is. We're going into the register and swap out on the other side. Okay, now we're switching to another program, and it swaps a lot of bytes. At this point, I could just go around and see the first one is 0C57. So if we go here, okay, 0C57. So it's inside this. If this looks like a head to you, that's an ear. So we need to stand here, 0C57, and we're waiting for the swap. And we're swapped out into the, well, let's call this an eye of the character. So now we want to stand. You see, there are 3 more swaps, and the last one goes to 025A. So 02 is all the way to the left into the neck of the character, and we want to go there. So we need to be at the previous swap, 1855. So we move to 1855. We're not there. It's gonna swap us to 1855. Okay, we're there now, 1855, and now we're waiting for the next swap. Okay, and we're going out. And this time the program itself jumps to another program. Oh no, it stays, sorry, it stays at the same program. Okay, now we get to the compare instruction. This can be a little bit confusing. What does this do? Well, compare instruction only sets the value of the compare register. So it takes the value from the data register, compares it to the byte next to the compare instruction, and then sets the value of the compare register. Later, we have conditional jumps, which jump if the compare register has some value. So let's see how this works. To go further, we need to remove these 4 bytes, and we can see the byte next to me I am at B17B, and that's B27B, and you can see it's the fifth instruction, swap B27B. This will remove the letter G from our way. So how do we get there? We need to make CPU execute the line with swap B27B, which is the line at address 8864, as you can see below the yellow arrow that shows the current line. So to get to the 8864, if you look at the program above, we see this instruction at 8862, which has jump equal, JE is short for jump equal 8864. So if the compare register contains the byte for the equal values, then it will jump there. So what does have to be equal? Well, this one. It compares the data register with 4040 hex, which is our player character. So in order for this to work, we have to swap ourselves into the data register, then compare will determine that data register is equal to 440. So it will set the compare register to equal value, and the program will jump to the next section and swap out the G letter. So all we have to do is find this address AE77. So it's somewhere around here. AE74757677. Here we are. Now we'll just wait. Swap out. We are in the data register, and as you can see, data register is 40, and this line, which will execute now, compares to 40, and since they are equal, it set the compare register to 0. So now jump equal, which checks if compare register is 0, will jump to 8864, which swap out the G character, and since we were in the data register, it swapped us out. So G is over there, and now let's see what's happening. G goes back to where we were, and now we see another set of swaps, which basically does the same thing but for the next obstacle, this letter A, and we have to go to AA76, and now we repeat this for the remaining letters. Now if you press B for a hint, you can actually see all these addresses highlighted. Okay, so let's swap out E, and done. This puzzle is solved. Let's move on. Okay, now we have a similar thing, but all the jumps, all the swap addresses are here, as you can see, inside this little box. So first, CF7B, let's see, CF, and we're at 79, we need to go to 7B, so that's below us. Okay, now we wait for the swap. Okay, it compares us, and it jumps back if the value is less. Since the value isn't less, it's equal, it will keep executing, so it will swap out the S character. Now, it looks like I could move up and escape, but I can't, because as you can see, the next swap will swap exactly the byte above me. So if I go above, it will swap me back into data register, and then it swaps me out here. So if you look at the hint, these two addresses here are just used to swap out the extra characters. Okay, so we need to remove the next one, CF77. So we go back to CF77, it swaps us out, done. And now we do the last one, actually we do the O, and we still got P, which moves itself. Okay, we don't have to stand anywhere. And now if you go this way, you reach the dead end, and the same program keeps executing, and you start thinking, did I mess up something? The fact is you didn't. This puzzle is special because you need to repeat the process twice to open the space above you. As you can see, these characters above the letter P don't have the 7-bit set, so I can go there, as I can go here as well. Okay, so we're just gonna repeat the process, but now an interesting thing happens. Letter S goes here. Okay, so we're redoing the process because the extra letters will now end up here and not back where they were, so we can pass them. Okay, let's do the other one. Okay, so T, and now we just need to remove O and we're done. Okay, O is done. Now if you spend too much time here, you could get stuck. Oh, I didn't manage to do it. If you do get stuck, you can go back and repeat it one more time and you would remove them. So it's a really special puzzle. Okay, so we're doing this one now. Now this one is tricky. If you press B, you can see all these swaps. There's so many of them, right? But if you look at them closer, you see they're all swapping the adjacent bytes. So they start with F186 and they go down to F0, EF, EE, ED, EC, EB, EA, E9, 8, 7. Then I do the comparison with 6D and they and if it's equal, the program will exit and basically let you through. So the question is, when does this happen? This last one, E786. E786. Let's see if we can find out. Can we go there? We cannot really go there. We can. So we can go there just to see. So this one. Okay, this one needs to be equal to 6D. And apparently it is not, even when we stand there. So this means that we don't have to stand there at all. What we need to do is find out which character is 6D, and we have to stand here. As you can see, the last swap before the value is compared to the player byte is F186. It's at address DC88. Let me see if I can show you. Okay, so this instruction, this is the last swap, and after that we have comparison if that's the player byte. So what we need to do is stand there to make sure the player byte gets compared, and we swap out to the final instructions, which is actually, let's see, where do we want to go? The last swap is at E586. If you look at the program, the last swap, it's not the last statement, but the last swap above the last statement. It's 8586. So 86 is here, and E5 is somewhere. You see, E5 is here. If you look at the register word or the hint word, it's below I in the hint word. So if we go down here, we can see that below I in the hint word, it's actually exiting to the left from these letters. So we need to make sure that this swap loads us. So we have to stand at F186, which is exactly here. Okay, so now it compares, it does some comparison. It doesn't matter which one. Okay, one of these letters, bigosori.com, is going to match, and when it does, we're gonna be here, and it's gonna swap us out to the other side. So now we just wait. Here it is. Okay, now we have a labyrinth. Basically, we just have to find these two addresses, C589, and it will swap us to D38D. So we can go around and try to find C5. Okay, C589 is basically 2 bytes below me, so I cannot go there. So I need to use this other address. In this puzzle, the order of swaps is reversed to confuse you. So you basically have to find this other address to get to this first address. Let's see, D38D. So it's somewhere around here. D38D. Okay, we're there. So now it swaps us into data register. There's some old compare values. So now it says jump equal, but the compare register isn't set yet. So this will be false. It won't jump here. It will jump back to the start. We are still inside the data register. It doesn't matter that the program just started executing from the start. So now it compares us and sets the compare register. It swapped us out. What happens now is really interesting. This swap just returns the value to the starting point, and now the compare register is set because we were there. So the program will start executing another program on the other side of the labyrinth. You see, the program changed, and this program that executes now, if I press B, there's nothing because we're yet to get there. So the rest of the labyrinth is just your regular labyrinth. You have to find your way out. Okay, we're out. Now it says hack. This is a different puzzle than any other we've seen before. We obviously have to go through here, and this byte to the left of us is 4C81, and we can see the swap for 4C81, you see, below the current instruction. So 6E81 is the address of the instruction that needs to swap this out. How do we get there? We have a problem, because this jump returns us back to the start and goes back. So we need to somehow trick this one not to jump. So how do we do that? We need to make sure this compare does not compare. Okay, doesn't make it less than. So what does it compare? It compares a byte at 3E7E. If we press B, we can see that's on the other side. You see, I'm at 7E now, and 3E is basically that empty byte over there. So it compares to the empty byte, which is 0. It compares 0 to 2E, this dot character. So it will always be less. 0 is always less than any other value. If I stand here, you see I'm changing the program now. Now it compares against 6E, or the small n letter, but it's still less. So this doesn't help us. What does help us is if we move here. Okay, now instead of fetching the byte from 3E 7E, it's fetching the byte from 7E 7E, and we're gonna go outside and try to find that address first. Okay, so you can see now it's taking the byte from there, but now it's taking the byte from somewhere else. So let's find 7E 7E, see what happens. Okay, 7E 7E is this one. See this dot over here? It will take the dot, and then it will compare it to the dot. Take the dot, compare it to the dot. They will be equal, not less, and because of that there won't be no jump and the swaps will happen. So let's do it. Okay, took the dot, compares it, jump fails, and now the swaps swap out the X and we can go further. Similar thing here, only this time, as you can see, I can enter some of these, but it doesn't change a thing. And as you can also see on the top of the screen, letter A keeps swapping in and out. Okay, what am I doing? I'm changing. So in this one I changed the swap address. In this one I cannot enter the swap address to change. What I can enter are a couple of these swaps here, but I cannot get to them, and I can enter the check. So what I'm doing is telling letter A to check against letter A. As you can see, when I stand on this, it turns into A. So they are equal, and it jumps to the final swaps and swaps out the characters so I can go forward. And now we get to the really tricky one. Okay, so for this one, if I press B, you can see that something will happen with this character. This I don't know, ceiling of the house here, if you consider this a small house. Okay, so the ceiling will move away and we will be able to enter inside. How do we move the ceiling? Let's see. The address of the ceiling, if you look at the top of the screen, is 1D84, and we can see that one. Swapping out 436F. So we need to find where that is. 436F is somewhere above us. You can see the A character on top flashing. Okay, so that swap does not concern us. What does concern us is how do we get past this point. You see, this one jumps to the beginning of the program. So what we need to do is somehow skip this jump. But how do we do that? We want to jump to 4182, but there's no jump to 4182, right? So the trick in this one will be to actually change the jump. You see, now we have jump to 4182. See? It says if equal, jump to 4182, which will unlock the ceiling of the house. So how do we make sure this is equal? Well, let's see. It's not equal now. What is it comparing? It's comparing the data register, which changes between 6E and 0. So we need to make sure that the data register is either 6E or the 2, but we need to be 2E. So what's the problem here? Well, if we stand on this dot over here, now it's 6E. Okay? It's the letter N. You see, it's swapping the letter N from the top. And if we stand here, we are comparing the letter N. So what do? We execute carefully now, okay? This one will fail because the letter N has returned to the top. So we have to wait for it to get here, okay? Now the letter N is inside and we are comparing against it, okay? Now the compare register is set to 0, which means equals. But if we stay here, it will jump to 0182, which is exactly what these little arrows are showing, you see? 0182, which jumps back here. Okay, so we need to trick the compare and then change the jump location one after the other. Okay, let's do it. Okay, so we swap in the N, check against it. Now the compare register is 0, and now we go down to change the jump location to 4182 before it executes. Okay, and it executed. Now we are 4182 and the ceiling of the house moved. Okay, now we can enter the house. Okay, now we need to learn a new instruction. It's very simple. It increases the data register by a certain value, and if you increase it more than can fit in a single byte, so more than 255, it will wrap around. So if you have 255, you add 1, it will become 0. You add 2, it will become 1. Okay, if you add 10 to 255, it will become 9. So basically, you can use this overflow to subtract as well. Okay, so this one is not a puzzle, it's just an example of a counter that uses the add instruction. Okay, and you can see here when it gets to 9, you will see this one, add F7, which basically means add 248, 247, so it will wrap and basically reduce it by 9, because 247 plus 9 is 256, which is exactly 1 byte. Okay, so this one is just for fun, nothing to solve. We move on to the first puzzle. Now this one says exit to the right. You can go to the left if you want to explore, but if we press B, we basically see everything that is interesting here. On the top, you can see that the position on the top where we can go, this one, is somehow related to the second code instruction. We will see why is that in a minute. Let's see what happens, okay? I got swapped out and swapped back, and something interesting happens. So for this puzzle we don't have to understand how the whole program works. We just need to know what's going on, okay? As long as I'm standing here, the code that checks if I'm here, you see there's compare 40, which is our character. It does something to the address, to the swap address in the second line of code. So it adds 1 to it. As long as I'm here, it adds 1. Why is this important? Well, if I hold B while doing this, you can see something interesting happening. You see? The swap address is moving to the right. And we have a wall here. So if I can move it past this wall, I can swap across. Okay? This here is EE address. You see ED, EE. Okay, so I need, the next one is EF and the next one is F0. So I need to get it in the F0 territory. So I'm just gonna stand here and wait for the second swap to go to F. Okay, it's F3 now. Okay, that's enough. So now I'm going here. You see, that's one of the addresses that gets swapped. BF B4, the first line of the code. So when I stand there, I'm gonna go into the data register, and then the next one will swap me out to F3B9, just like we want. Okay, so I'm inside and I'm going to the other side. That's it. Okay, we have an interesting one here. Now this puzzle is tricky because it has 3 parts. The code has 3 parts basically. There's this starting code that basically just checks F2C2, which is the byte above us, which we cannot reach. Okay, compares it to 39, which is this here. You see, that's digit 9, ASCII digit 9. Okay, so it compares to 9. Basically it comes to 9. Once it's 9, it does a bunch of other comparisons. It checks if it's greater, equal or less. So if it was less, wait, if it were less, like now, it would go to this code here. You see a small part of the code on the other side. Okay, so this code here adds 1. Let me just go back to it. Okay, returns the value back and jumps to the first code. So we have 2 programs executing here. This one just adds 1 and goes back. This other one counts to 9. If it is 9, it's 6, 7, 8, 9. Okay, so it's 9 now. When it's 9, it does a bunch of other comparisons and does this, add F7, which, as we've seen before, just subtracts 9. So it goes back to being 0. Okay, what do we want here? Well, we're gonna start backwards. Okay, we need this removed, this obstacle. And this obstacle is at address EDCE. And we can see that at F0D2. So how do we get to F0D2? Well, that's a tricky one. Let's see. We have a jump to F0D1 somewhere in the middle at FOCA. So basically, to get there, we will need to have jump to FOC9, and comparison with A0 will have to be greater. So how do we do this? How do we get to FOC9? Well, comparison has to be greater here at FOC6. Okay, so we just need a value that is greater than A0 and the puzzle is solved. Now, how do we get the value to be greater than A0 when the program just goes to 39 and restarts? We have to trick it. We can change 2 things. Okay, we can change this, which adds 1, and we can add 41. Okay, if we do that, you see data is now 37. Now it's 78. What happens here, though? That's the problem. It's greater than 39. So it will go here, but it's not greater than A0. So this will fail, and it will reduce it by 9 and restart. Okay? So now when it compares, it's going to do the same, and it's preventing us from getting the value increased further because it keeps reducing it by 9, and our code, our modified code, never gets executed. So what we need to do, you see, it will go all the way back. So what we need to do, and the only other thing we can do, is to trick it here. Instead of comparing to 39, we'll tell it to compare to 79. Okay, 79. This will let the value increase much further. So I'm just gonna hold this one and let it execute by 1 until we get close enough to A0. Okay. Okay, I think this is good enough. Now what we need to do here, I cannot leave this place because it's 6E now, and if I leave, it will just reduce it back. So I'm doing this one more. Okay, now it's 6E, and I have just enough time to walk over to the increase value byte and stand on it just before it increases by 1 and let it increase by 41. Okay, and now the data register is AF, which is more than A0, and the rest will happen by itself. Okay, done. Now we have a really simple puzzle. This one is great. If you had trouble with this one and the previous one, I suggest you maybe skip this part of the video, because this one is really easy and really sweet. Only 4 instructions, really easy to understand. So if you want to skip it and try it yourself, if not, here we go. So what does this do? It swaps. If you press B, we don't see anything. It swaps some byte away from the screen, adds exactly A0, which is 128, and swaps it back. 128, if you add it twice, it means you're adding 256, so you're back at the byte that was before. So what do we need to do here? Well, we cannot go through here, and we want to swap this one out. It's C2CE, and we can see something interesting. 8-2CE, and we need C2CE. That's exactly 40 of difference in hex, 64 in decimal. So if I stand on this one or the other one, I'm gonna swap the byte here. So let's do that, okay? I'm just gonna stand here. Okay, swap it out. Nothing happened. Interesting. Okay, swap it back out there. Nothing is happening. Oh, something is happening. We have something here. Let's see. Can we go through this one? No. Okay, let's try again. Let's swap this out. And now add to it. No. Okay, we're in deep trouble. Okay, what we need to do actually is we need to manipulate this one as well. Add. We want add, not to add 128. We want to add more, so the byte changes and let us pass. Let's see. We're gonna add this and then swap that here so we can see what's going on. Okay, that's X. That's bad. Okay, so let's do it again. Swap, add. Okay, this one is promising. Can we go through this one? Yes. Okay, but now pass through here, and this is exactly 82CE, so that's the other address. Okay, so now we may need to make sure that we swap out A2CE and pass. Okay, what do? We take A2CE, add a different value, which will change the 7-bit, and swap it back. Okay, this should be enough. Okay, we can pass through this one. Done. Now this one is really cute. It's called It's Time to Calculate. It's also easier puzzle. Basically, as you can see, this byte just gets increased by 1. And code is waiting for it to become 3-8. As you can see, this is the line of code. So compare 8, it compares with ASCII digit 8, which is 3-8 in hex. So we somehow need to make sure that it says 5 plus 3 equals 8, but it never gets there. Why? Because as soon as you see, it adds 1, compares, if it's greater, goes here, swaps it back out, and jumps. Okay, so now we're waiting for the value to wrap around, right? F, E, F, F. Okay, next one's gonna be 0. So it's 0 now. Compares to 38. Is it greater? No. Is it equal? No. Well then, we just add number 9, which basically skips over the first 38 values and restarts from 9. So we never get to see 1, 2, 3, 4, 5, 6, 7, 8 because it skips that at the beginning. What we need to do, and what we can do, we can do this one and let it go to 79, but it doesn't help us at all, because once it wraps around, it's gonna just, you know, get moved by 39, and then we're never gonna get that low. So how do we get that low? Well, for this one we need to use the wrapping, and we need to calculate precisely, because we can change this one. Instead of adding 1, we can add 41, which is that's 41 hex, which is 64 plus 1, that's 65 decimal. So in order to get there, as you can see, we're not getting anywhere with this either, but if we were to do it at the right time, it will succeed. So when do we need to do it? That's why the puzzle is called It's Time to Calculate. We need to calculate which number we have to add 65 to get the 38 hex. Okay, so 38 hex, I think you need a pen and paper calculator for this one. Okay, 38 hex and 41 hex. Basically that's the difference. We're adding 41 to something to get 38. So if these were decimal numbers, okay, you would take a number that is 3 below 3. So imagine you need to get 138, and you're adding 41 to a number to get 138. So you would take 97, right? 97 plus 41 equals 138. Okay, now we need to do this in hexadecimal. Easiest way is just to convert to decimal and then convert back. Okay, so 41 is actually 65, and 38 is let's see, 48 plus 8, 56. So between 56 and 65 we have 9. Okay, so do we have 9? Let me see. We want 38 and 48. We have 16 minus 7. Yeah, that's 9. Okay, so now we need to calculate 256 minus 9. Okay, so if 255 is FF, okay, 255 minus 8 is F7. Okay, so once the value is f7, we add 41 and it will be exactly 38 and the door will open. Okay, so let's go. Just let this, actually we can speed it up a little bit. Okay, 93 d4. Okay, now we're waiting for f7. 3 4 5 6 f7. Okay, we can stand here now. Plus 4 1 is exactly 38. Okay, and now when we step aside, the equals is true and the program can go on and let us pass. Okay, now this one is really tough if you're just trying to understand it, so don't. There's a hint here which says don't waste your time trying to understand everything. All this code here just does one little thing, so just focus on replacing the bad code instructions with the proper one, and you can see this here says bug is here. You can see these lines, and if you press B, you can see something really interesting. Okay, this program just checks where the player is standing, and then it will replace the instruction at the end with the one the player picks here. Okay, so which one do we need? As you can see, we have the compare, add, greater than, equal, and less than. And less than is already here, so let's try. If I compare it with equal, you see, now we have C here. Now compare is here. But what do we need here? Which instruction do we need here? Let's go back a little bit and see. If we return this one here, okay, you see, it says jump less. So if less than something, jump to 00 C9. And here's a hint clearing the path which says 00 C9. Take the empty star, replace the obstacle, move it away, and jump to next program. So we need to make sure that jump at the very end of the program will happen. When will it happen? Let's see. It doesn't happen when it's less, we know that. What is the value of the compare register when we get there? Let's see. There are two compares in the code. Okay, first one is here, which is just the counter that moves this checker, so it goes to 5 and then restarts. And the other compare compares us with the player when we get here on one of these, so it will be equal. So what we need is to put the equal instruction there, which is the letter E. Let's do it. Okay. Okay, it's gonna swap us out. Set the compare to equal. It is equal. It does a bunch of swaps, which we don't care about. And now says, is it equal? Go there. Okay, it goes there, swaps out the obstacle, and we can pass. Okay, and now introducing page. Okay, the game is actually really short and it takes a lot of time to figure the puzzles out, so don't worry, we're only like 3 or 4 puzzles away from the end. Okay, this one swaps to 3AFA, so we're just gonna stand there. Yeah, we're here. Jump there, and now it executes the page instruction. The page instruction moves us to a different page. Okay, we're here, swaps us out, and we're out. Okay, so you can see at the top of the screen it says player location system RAM page 2, and you can see the page register on the right side which says 2. Okay, so we are now in the memory page number 2. All of these are walled out, so we are reading these instructions. It says press A to flip between the pages you already visited. Okay, so if I press A, I can go back to page 42. As you can see on the right side, the page register still shows 2, and the program is grayed out. So programs are not executing if we're not there. Okay? This one is pretty much rolled out as well. So what do we do now? We're gonna flip the pages to escape. Okay, no way through here. I'm not even sure where I want to go. Let's press B. Okay, I can see some instructions executing down there, and since there's nowhere else to go here, we can try to swap our way there. Okay, we're here now. What does this do? If we change the swap, nothing happens. What if we change the jump location? Okay, we got a new program executing. It does some comparison and jumps to another program, and this one looks stable, and it's at 40E2. It swaps at 40, and the program it says at 4F, so we cannot get to the program, but we could get to the swapping byte. Let's see what's happened and what's gonna happen there. Okay, so we swap back up, find our way to 40E2, which is here, and now it just swaps us back. So what the hell is going on, right? Well, watch closely. We're now in the data register, and the page register is no longer locked, because it used to be page 42 and we couldn't move there because that 7th bit was set, but now we can move across registers. Okay, so this is a huge change, and now I can swap the page register myself. Okay, I swapped the CPU page register, and now it's executing code in page 42. Okay, so if I let this code execute, it will swap out this byte. Okay, now I go back to the data register, and the CPU goes back to executing code at page 2, lets me out, and now I can swap myself here. Okay, now there's a byte here which doesn't have the 7-bit set, and I cannot go through here, but I can go through here. Okay, so these two puzzles where you have to change the page register are somewhat hidden because it's near the end of the game. Okay, let's see. I cannot pass through here, but I can pass through here. Okay, so 66FA is in front of me. I'm just gonna stand on it, see what happens. Compares to 0, which doesn't really matter apparently, and it jumps back. Okay, so I probably need to change the page register again. Okay, this one is even worse. Okay, so what am I doing wrong? Well, nothing. The thing is, you can do this. We want to avoid this jump. Okay, so we go to the page register and then we go back. Okay, now it swaps us here and doesn't look like we can go anywhere from here, but it says flip page for a hint, and if we do that, okay, we get a reminder how the compare and jump instructions exactly work. Okay, we can see something interesting here. It says compare register 0 and equal, 1 when greater than, and all ones 255 when less than. We will use this. There's no way to escape from here, by the way. I did have an idea for a secret achievement if you run away from this, but you cannot. I mean, you can swap and try, but this is a lockdown. Okay, so we're going back here. We're getting our ass swapped back, but we're gonna change the page register. Okay, so now we execute this carefully. Okay, this jump we don't want to do. It's gonna get us back to the beginning. So we escape. We can go either to the data register or the compare register. We tried the data register, it didn't work, so we go to compare. Okay, it says jump when less to 5BE6, which is exactly what we need, but it didn't happen before because we weren't in the compare register. Now we are, and the rules just said if the value is 0, it's equal. If the value is 1, it's greater than, and if it's any other value, it's less than. And it's exactly any other value because we are there, and it's the value is like 64, 40 hex. So it's gonna jump there, and now it's gonna swap out the data byte to another location, which will let the player escape. But there's a problem. We aren't in the data register. So how do we do this? Well, let's try to get to the data register. We're gonna switch the page, doing it. Luckily, this jump on 5BE6 only jumped to 5BE7. It didn't restart the program, and now we can go to data register, and the code on page 02 will swap us out back into the RAM. Okay, here it is, and swap. Okay, we're now on the other side of this obstacle, and that was the final puzzle of Rogue Bit. This is the end of the game. Once you enter this byte, the game closes and the print dialog opens up, asking you to print this page with this byte in it, and you can basically print it and have your rogue bit turn into ink on the paper and become real, which was the goal of the game. Thank you for watching, and feel free to leave any comments if you like to see some improvement to the game or maybe changes. I don't know. Thank you.